So in this video, we are going to prove the most important theorem in your study of single variable calculus. That's quite the statement, but the fundamental theorem of calculus is just that. It is fundamental to calculus. And what we're going to do is, based on the area functions that we defined previously, we're going to prove this theorem. Now, actually, we're going to prove one version of the theorem in this video, and then a second version in a subsequent video. So let's get started. So just as a reminder, so the idea is we have a function, and we're using t as the variable for this function. And this function is continuous on the interval a to x, right? And then we define the area function to be, again, the integral from a to x of f of t dt. So again, just as a reminder, here is our function y equals f of t. Here is our t-axis. And then along the t-axis, we have two numbers, if you will. A is a constant, and x is our variable. And the area function gives us this area, right? So what we're going to do, essentially, we want to know, like in general, what's going to happen if we take the derivative of this area function, right? So recall, before we got to fancy rules for derivatives, all we had was a limit definition. So remember, and in fact, we had different variations of our limit definition, but this was the one we kind of settled on. So if I wanted to know what the derivative of this function is, the limit definition says I would have to take the limit as h approaches 0 of a of x plus h minus a of x all over h, right? This is our limit definition for the derivative. So for this area function, we're going to have to compute this difference quotient and then take a limit at the end and see what we come up with, right? So let's start by looking at the expression that's in the numerator. Let's look at the ax plus h minus a of x. Well, so if we by definition, a of x plus h is the integral from a to x plus h, that's of f of t dt, and then minus, again, by definition, the integral from a to x, and then f of t dt. So if h is positive, right? So if h is positive, let me draw kind of what's going on here, right? So if h is greater than 0, so let me put a, let me put x, and then if h is positive, then x plus h would be further to the right. So it would look like that. And again, remember, that's our t-axis. So we have our thing here. This is our function. So the first, the a of x plus h, that gives the area under this function from a up to x plus h, right? So it gives this. And then the second integral gives the area, again, under the curve, but now going from a and it goes up to x. So it's right here. So that one. So if we take a difference between these two, so if we take the blue area and subtract the red area, I'm going to be left with the green area. Right? In fact, we illustrated this property earlier with the area function, that if you wanted a different the area of a different region where the lower limit is a, you can take the difference between the larger area and the smaller area, and then you're going to be left with that part. So what this means is the a of x plus h minus a of x is equal to the integral. So it's another area, but now the region is between the t values of x and x plus h, but it's still under the same graph, f of t, right? And in fact, not only did we illustrate this with the area function, but this is one of our properties of the definite integral, right? So this is also a property. So we've seen this in several variations previously, right? So now what I'm going to do is draw this. I'm just going to draw another area that illustrates just this. So basically the green, I'm going to draw it like in an expanded form so you can see it a little bit more clearly, right? So here is the graph. And f of t dt. And so let's say this is x, and then let's say this is x plus h. And again, so let me shade it also in green so it's consistent with the shading above. Now, if I take, for instance, let's say we're doing like a left Riemann sum, and I take this rectangle. So if I take this as my x value and I form my rectangle, then this smaller rectangle, or this small rectangle, has less area under it than the curve, right? And similarly, if I took this big rectangle, where would I use this as my x value and then that as the height of the rectangle? So if I take the right endpoint, evaluate it in my function, and make this rectangle that goes above it, then that rectangle, all of this, has an area that's bigger than the area shaded in green, right? So now for that to be true, right, we're going to assume that the function is increasing. Now if the function is decreasing, you switch the logic, right? But so if f of x is increasing, right, then, so what is it? The area of the small rectangle is f of x times h. That's the width, right? So we would have f of x times h, right? And then that would be less than or equal to the area under the curve, which what we showed earlier, that was the difference. That was the a of x plus h minus a of x, right? And then if we take the larger of the two function values, so if we take the function and evaluate it at x plus h, that will give me that height, and if I multiply it by h, which is the length of this interval, I will get an area that's bigger than the area in green. So then that's less than or equal to f of x plus h times h, right? So we have this inequality, and again, since h is greater than 0, I can divide this inequality by h, and I don't have to change the symbols. So this implies, oh, not h, f of x. So f of x is less than or equal to this whole difference, but now divided by h. And hopefully you see where this is going, right? And then that's less than f of x plus h. And now we have our difference quotient. So if we can take the limit of each part of this inequality, right? So let's do this. So if we take the limit as h approaches 0 of that part, then that would be less than or equal to the limit as h approaches 0 of the whole difference quotient, which is our definition of the derivative, right? And then that's less than or equal to the limit as h approaches 0 of f of x plus h, right? And what we're essentially using is that wonderful squeeze theorem from Calc 1, right? So we have this inequality. So now let's see what's going to happen. Well, this limit here, as h approaches 0, there is no h in this expression. It's just f of x. So it's almost like this is you're taking the limit of something that is independent of h. So no matter how small h is, this isn't going to be affected. So this is f of x. And then we have our derivative in the middle. And then what about this one? Well, here we would have to plug h equals 0 in, and then we would have f of x plus 0. And we can do this because f is continuous. That's the definition of continuity, right? So this is by continuity. But what do we have here? So f of x is less than or equal to a prime of x, which is in turn less than or equal to f of x. So the derivative of our area function is squeezed between f of x and f of x. So by the squeeze theorem, our a prime of x is equal to f of x, right? Now here we made some assumptions that the function is increasing and also that h is positive. Those assumptions can be dropped. We essentially would just have to redo the logic with slightly different inequalities and so forth, but the conclusion would be the same, right? And this is our fundamental theorem. So let me actually state the theorem now in all its glory, right? So this is our theorem. And this is and it's abbreviated FTC, and this is part 1, right? Because there are two versions of it, and it says this: assume that f of x is continuous on an open interval, right? So some interval, and let a be in that interval, and let the number a be in that interval. And this is the a that's the lower limit, right? So then the area function All right, so then, actually, let me say, instead of saying then, let me start it this way. If a of x is equal to, and then we have our area function there, f of t dt, then, which is the conclusion, the derivative of the area function, so, and it's written several ways. You can use the a prime notation like that. Sometimes you'll see it in a slightly more complicated way where they put the d dx in front of the integral sign. And then we have this. But the whole idea is when you differentiate this area function, you get back the original function, right? And that's what the theorem states, right? So, it's on one hand, it's a very kind of theoretical result. Just trying to wrap your mind around these area functions might not be the easiest thing. And then, so it's a function that it's hard for you to conceptualize, and then you're trying to take its derivative, right? Which again might add another layer of complexity, but it's basically saying that. So in words, what this is saying. And we saw this earlier when we kind of illustrated and actually computed one of these area functions. A of x is an antiderivative of f of x. Right? That's so in a nutshell, a of x is an antiderivative. Okay, let's do a couple examples to wrap this up. I don't want this video to be just the proof, or at least a partial proof, but we want to see like how do we actually use this. So let's look at a couple examples. And so here is our first area function. It's the integral from 2 to x, and the function here is the square root of 1 plus t cubed dt. Right? And let's go through and find a couple things. So the first thing that we're going to compute is this, a of 2. So if we plug 2 in, right, for all the x's, it will be the integral from 2 to 2 of that square root, right? But this is one of our properties. One of our properties of the definite integral says when the lower and upper limits are equal, our function is nice and continuous, and this function is continuous on the interval like t greater than or equal to 2, then this integral has to be equal to 0, right? So that one's pretty easy. Now, what if we had to differentiate this area function? What if we had to find a prime of x? Well, to find a prime of x, again, we would differentiate the integral. And what would happen is, again, this version of the fundamental theorem, it's basically telling us that, integration and differentiation are inverse operations, which we already knew because that's kind of why we defined antiderivatives that way. We were kind of leading to this theorem. But if you're differentiating an area function, you're gonna get back the original function, but with x as your variable, not t. So the derivative of this integral, this area function, is the square root of 1 plus x cubed, right? And then if you wanted to evaluate this derivative, you would do it the same way. So now let's say we wanted to find a prime of 2. So now we would plug 2 into this part, right, just the square root, so this would be the square root of 1 plus 2 cubed. So this is 1 plus 8, square root of 9 is 3. And what's nice about this is we can continue doing this differentiation. If I wanted to find the second derivative of this, like a double prime of x, now that means I would differentiate this root, right? So then it would be the derivative of the square root of 1 plus x cubed. And then for this, we would need our chain rule. Let me rewrite it so that you can see it. So we have 1 plus x cubed all to the 1/2 power. Using our chain rule, that gives us 1/2 times the quantity 1 plus x cubed minus 1/2 times the derivative of the inner, which would be 3x squared. So writing this with positive exponents, so what do we have? In the numerator we'll have 3x squared, and then in the denominator we'll have this 2, right? That's in the denominator of this fraction. Taking the reciprocal gets rid of the negative exponent, and then that 1/2 exponent can be written as a square root, so it looks like this. Right, so that's its second derivative. So the whole point of this version of the theorem is that yes, we have these area functions, but as far as differentiating them, right, to find, for instance, the first derivative of an area function, we use the fundamental theorem that we just established. If we have to differentiate that function repeatedly, then we might have to use other rules. In this case, we had to use the chain rule, and so on. All right, let's do one more, and let's see. So another example. Now, do we have to use a of x? No, we start using a of x because we're associating this function with area, but it could be any letter. It could be g of x, and it could be from 1 to x, and then the sine of t squared dt, right? And if we wanted to find the derivative of g of x, so g prime is the derivative of my area function, and the fundamental theorem, this really powerful theorem, tells us that we're going to get back the original evaluated at x. Got a bug in my throat here, so sine of x squared, right? And again, if we wanted to, we could repeatedly differentiate it. Just for fun, let's find our second derivative. So this again will require the chain rule, but now the derivative of sine is cosine. Keep the inner function and then multiply by the derivative of the inner, so we end up with 2x cosine of x squared, right? So this is our fundamental theorem part 1, and it's seemingly a pretty theoretical result, but in the subsequent video we will see there's a part 2 to this, which gives us the process that we need to be able to find areas exactly, and it all comes down to antiderivatives. Sure, you can't wait to see that. So I'll see you in the next video.